you actually get in on the roster, or you're not sure yet?
I don't think I'm on the roster yet.
Okay. Just keep checking.
Okay.
You can keep showing up until you know for sure where you are. So today's still going to be a very light day. I mean, we're going to be doing some stuff, but we're not seriously in calculus yet. We are going to do a review of exponents and logarithms. Have you all seen this before? Familiar with exponential and logarithms and all that stuff? Let's talk about the laws of exponents first. Right, so exponents, sometimes called powers. So there's a notation. So something like x to the a, you write it as it's called a superscript. This here is called the exponent. And the thing at the bottom is called the base. So this is an exponential expression. You write the exponent in the upper right corner, and the base is the thing at the bottom, to the left. And so now we have some laws I want to remind you about how exponents work. One. If you multiply things of the same base, how do you compute that? Yeah.
You're adding them.
You add the powers. This is because the exponents, at least with integers, we do extend them to other numbers, but at least with integers, positive integers, it tells you how many times you want to multiply the expression. So this is if a is a positive integer, which is just a positive whole number. This basically is shorthand for just multiplying x by itself a times. Right? For other numbers, it might mean something slightly different, but that's basically it. And so what you can think of this is just x being multiplied by itself a times, multiplied by x being multiplied by itself b times. When you count up the total number of times x is being multiplied by itself, it's a plus b times. Similarly, you can have, what if you're dividing? Yeah,
Subtracting.
that's when you subtract the powers. And here, x is not 0, because you can't divide by 0. 3. What if we have something to a power raised to another power? Yeah,
You multiply them.
now you multiply it. So you guys are answering pretty fast. I don't think I have to really do any examples here. I just want to make sure that you're aware of all these rules. What's another one? What about x to, let's say it's a negative power? Yeah.
You go x is equal to, like, it becomes x 1 over a, so 1 over a.
X to the 1 over a? No. Yeah.
Goes 1 to the x, 1 over x to a.
Right. That means that. Okay? So you don't take the reciprocal of the power, it means the reciprocal of the thing. And notice here, there's no sign change. Negatives in the power do not make a sign change down here. So that's something that's important. All right, and another way, well, 5, about things like this. X to the 1. It's just x. It's like you're multiplying x by itself one time. What about x to the 0?
1.
It is 1, provided that x itself is not 0. One way you can do this is realize that if you set a equals to b here, you get x to the a minus a will give you 0, and so you get x to the a over x to the a, that cancels and becomes 1. Okay, so that's consistent here. What about x to the a divided by b? Yeah.
You do the root of the top number and do the square root of the bottom number. For example, it was like 2 over 2, not almost 2 over 2, it was like 3 over 2. You put it to the third power and then do the exact square root.
Right. Okay, so this is the b root of x to the a, which is equal to the b root of x raised to the a, and it's interchangeable once x is positive. Okay, so what is that? Do you hear that? Or is that me? For the most part, it's interchangeable, so when you're really working on something, you can kind of alternate how you're looking at that expression. So for example, I can look at something like 9 to the 3 over 2. Right? Now there are a couple ways I can think about that. I can think about that as the square root of 9 cubed, or I can think about that as the square root of 9 cubed. Now both of these will give you the same answer, but one is more easier to deal with than the other one. Clearly this one is more easier, because finding the square root of 9, that's just 3, and then 3 cubed is 27. That'll be easier than cubing the 9 first. You have to remember what is 9 times 9 times 9, and then you have to take the square root of a bigger number. So you can interchange them. When the base is positive, you can interchange them at will. If the base is negative, you have to worry about whether this number is even or odd. It may or may not make sense. So we have that, and you probably don't need this, but one way I like to remember this is called flower power. We're going to imagine this guy is a flower, where the bottom is the root, the top is the flower, which rhymes with power. Hence, flower power is how you do it. And so you always know that the number in the bottom is the one that goes on the root, the radical. It's the one that's on here. And the number at the top is the flower, it rhymes with power, that's always the power. What else? We do also have distributive laws. Remember that powers do not distribute across sums, but they do distribute across products and divisions. So probably law 8 would be something like, you should know that if I have x times y, raising both to a power, this is just raising x to the power and y to the power. And if I have x divided by y raised to a power, the same as raising the top to the power and raising the bottom to the power. Right? This is not true if you put a plus sign or a minus sign here, that doesn't work, but with multiplication and division, that works. Function of the form, say y equals a to the x, is called an exponential function. It's a very important kind of function, and there's one of these functions that's in particular very important, but this is called an exponential function. Algebraically, they obey all the above rules. So you can multiply two exponential functions, and the new function will be created in a similar way like this, or according to the other rules. So you can manipulate exponential functions just like you can manipulate exponentials, exponents for numbers. That's important to know. As well as another thing that I want you to remember is the graph of an exponential function. So let's say y is equal to a to the x. Let's assume for the time being that a is greater than 1. A is negative is kind of tricky. A is 0. The function itself is just 0. If a is between 0 and 1, you can just apply what I'm telling you here to the value 1 divided by some number bigger than 1. So remember what this looks like? Picture? What does the picture look like? You remember? So exponential functions is not something you guys have seen before? You just seen this stuff? Okay. So if you were to graph something like that, and it's, let me make sure you know here, a is a constant. X is the independent variable. That's important to know. So let's say we're graphing this on the xy plane. This is your x, this is your y. An exponential function has this behavior. Okay. In this way, it'll always pass through the number 1. Again, because when x is 0, you have a to the 0, and our rules tells us that's 1, and it has this behavior. It increases very rapidly. In fact, it will increase faster than any polynomial eventually, and it decreases as your x becomes negative and starts getting more negative, and it approaches the x-axis asymptotically. It means it's never going to touch it. It just keeps getting closer and closer forever. So some properties that we have here is the fact that as your x gets larger, as your x approaches infinity, your function will approach infinity. As your x approaches negative infinity, your function will approach the number 0, getting closer to that. And we'll have a nicer notation for this later. But that's what an exponential function would look like. Now, you can transform exponential functions just like any other function. They obey all the shifting and stretching rules in pretty much the same way that any other function would. So you can actually have transformations of this function. So you could have something like y equals minus a to the x. So let's say you have an exponential function, but you take its negative. So what happens to that function if you multiply by a negative sign in front? What would that do? Let's see, because that's a general. It would flip it where?
Over the x-axis?
It reflects over the x-axis. So if you have a function and you make it negative, what happens graphically is that it flips it over the x-axis. So that's what that function would look like. This is a transformation, reflection over the x-axis. What happens if you negate the independent variable? So I made the x negative. Well, that's also a reflection transformation. That flips it over the y-axis. So that function would look like that. And of course, you can actually combine these two. So your function y equals minus 8 and minus x. That would look like this. So this is the behavior of the exponential function. You should kind of have this kind of picture in your head whenever you see a function like this. And remember, your a is a number, it's a constant. Okay? It's a constant value. If this is also a variable, it has some x's in it, it's a different kind of function. We don't really call it an exponential function. What else do I want to tell you? You can generalize this function. So example, I can write y equals a number times a to the x, or y equals a number times a to the x plus some other number, right? And these also have properties that you can kind of see in the graph. Multiplying by b stretches or shrinks the graph, while adding a number can shift it up or shift it down. So, example, so y equals 2 to the x, y equals 3 times 2 to the x, or y equals 4 times 2 to the x plus 7 are exponential functions. As you can see here, the power of x does not apply to the 3. If I wanted it to apply to the 3, I would use parentheses. So you should be aware that if someone writes down something like this, the power of x only applies to the 2, not to the 3. Parentheses would indicate otherwise. These are all exponential functions, so the graph of this does look like that. The graph of this would look like that as well, but it would increase a lot faster. And the graph of this would be shifted up by 7. So the new baseline would be at 7, and it would be increasing by that. I expect you to be able to manipulate functions in this way. Here's a very important kind of exponential function. It's definitely the most important exponential function in calculus. It's probably the most important function in all of calculus. And there are some mathematicians who think it's the most important function in general. This is the function y equals e to the x. This is called a natural exponential function. In fact, at some level of math, once you say an exponential function, this is what everyone thinks about, and everyone just assumes that's the guy you're talking about. It is the most natural function to use for calculus, and it's a super important kind of function. E is a constant, in case you didn't know. Yes, it's a letter of the alphabet, but it represents a constant. Kind of like how pi represents a constant. When you see the symbol pi, it's a letter of the Greek alphabet, but it actually means a number to you. E is the same way. So E is 2.71828. In general, it is irrational. It means it cannot be written as a fraction. It was discovered by Euler, or I should say it's named after Euler. So that's fair. I don't know if he was the first guy to ever come up with it. Euler is a Swiss mathematician, and he's one of the best mathematicians to ever live, and he was highly prolific even in his old age, which is kind of weird. most mathematicians back in the day, they kind of bottomed out when they were very young. In their early 20s was the height of their career. This guy, into his very old age, was just cranking out theorems like nothing. He invented numbers, and this number is named after him. And he came up with this number when he was investigating compound interest, and he kind of considered the idea, what if you had a fake bank account that pays you 100% interest, compounded, and it's compounded an infinite number of times throughout the year. If you put $1 in such an account, how much money will you have at the end of the year? This happens to be the answer. Right? If you put $1 in such an account, at the end of the year, you'll have $2.72 roughly. And so that's how it was born from compound interest. So the idea is the value of $1 goes into an account compounded. The phrase is compounded continuously. This means an infinite number of times. With a 100% interest rate. And that would be the value, because you'll have E dollars in this account. And in this sense, you have E is equal to that way. E to the x is the x. As x goes to infinity. And we'll see better notation for this later. A lot of the things I just mentioned when I'm using infinity, we're going to rephrase these in limits later on. Okay. So that's a very important number. It is called the constant E. This is where it comes from. And when you make it into an exponential function, by putting the power of x in it, it becomes the most important exponential function for calculus, and we'll see why this is the case pretty soon. But again, its graph looks just like a normal exponential function's graph. It passes through 1, and it increases at a certain rate. By the way, the larger the base is, the more steep this function is. That's how it would be effective. Just mention that, by the way, larger the base, the faster the exponential function increases. So, for example, if you were to plot them on the same pair of axes, let's say I made that y equals 2 to the x, then y equals 3 to the x would behave like this. It would get, first of all, a lot steeper, it would get a lot bigger, a lot faster, and it would also get a lot smaller, a lot faster. Right? So in general, it has the same shape, but it will increase and decrease faster. And so, make this y equals, say, 3 to the x. And the bigger the base is, the faster this will happen. So the function e to the x is kind of somewhere in between these two. Okay? That's an exponential function. Super important function. I'm going to actually use this function to derive a lot of the formulas that we're going to use for calculus. And there are so many things connected to this number, it is not fun. To this function in particular. It's a very important exponential function. So this little review is not meant to be comprehensive at all. And especially if you're not as familiar with exponential functions, you probably do want to consult the suggested exercises in the syllabus. Remember, in the list of topics that we have at the back of the syllabus, I also told you problems in the textbook that you might want to look at. So if you've seen all this before, this is probably good enough to start jogging your memory about how things work, but especially if you're unfamiliar with anything I just said, you probably do want to consult the textbook, because I'm not really going to go into detail here. It is kind of something that I expect you to have prior knowledge of. But I don't expect you to be as much of an expert with this as I do expect you to be with functions in general. So that's why I'm doing a mini review here. Let's actually talk about logarithms now. Now, logarithms are a nice way to rewrite exponential equations. Right? So that's equations that have exponentials involved in them. The definition is the following. Sometimes called log for short. I think it's the vending machine. Has anyone seen logs before? Okay. So I don't know if you've seen log functions before, but okay. So for the most part, this is probably a little review. The log of a number to a given base is the power. So a log is an exponent, but you're kind of looking at it from a different angle. So logs and exponentials are very intimately linked. I'll describe their relationship in full to you shortly. But the log of a number to some given base is the power to which the base must be raised to give the number. Segue into notation here. Locationally speaking, you write here a log of a number. A log can have a certain base, which you'd write that number down here. So the number would be written in this position. So this is log to this base of that number. It is equal to a power, to which the base must be raised to give the number. So this is just another way of expressing this relationship. The base would be the big number at the bottom, the power would be up here, and the number would be on the other side. I.e., the notation here will be log to the base a of b equals c. So a is the base of the log. C is the power that this base must be raised to give b. So for example, log to the base 2 of 8 is what? 3. Because I have to raise 2 to the power 3 to get 8. right? And I can express that idea by writing down that notation. That's what log is. Okay. Now logs also have their laws. And I'll talk about log functions pretty soon, but let's talk about those rules that they have. That was like the list of rules that I gave you for examples that I do expect you to remember from this point on. So one, the first rule is kind of just the definition, basically. But written in symbols, it's good to know it as a rule in itself. So basically we say log to the base a of b is equal to c if and only if a raised to the c will give you b. So these two, you should know, mean exactly the same thing. It's just another way of looking at it. Instead of making b the subject of the formula, we're making c the subject of the formula. So if I have an expression like this, and I want to solve for the number c, I would use a logarithm to solve for that number. Right? It's a way to solve for the exponential in an equation. So that's the first rule of logarithms. Now, once you know a log represents a power, this comes with other consequences. Let's talk about that in rule 2. Log to the base a of some number raised to a power is actually equal to the number times the log. So if inside your logarithm you have something raised to a power, you can actually take that power, move it down in front, and multiply the original logarithm, and that is an equivalent number. And this is kind of like, because the log already represents a power, this is basically saying we have something to a power being raised to another power. What do? You multiply the powers. The log was the original power. Right? So a log allows us to take an exponential form and turn it into a multiplication form, which is why we go through the whole hassle. You're like, well, we've been using this forever. Why do we need this new cumbersome, complicated notation? It actually breaks down a lot of our calculations to something a lot nicer to deal with. So instead of raising things to powers, I'm now in a situation where I'm just multiplying two numbers. Another way logs can be useful. So logs turn powers into products. They also turn products. Right? So let's say inside my log I have a multiplication going. Does anyone remember what that does? Yeah?
Addition.
It turns multiplication into addition. So the log of a product is actually the sum of the logs. So if I have log of something being multiplied, I can actually break this apart into a sum. And this is because if I multiply things of the same base, I'm adding the powers. In a similar fashion, I can have log of a division. Now if I have log of a division, that is the subtraction of the logs. So I can turn an expression like this into an expression like that, and vice versa. Another important property is that this is called the change of base formula. Which basically says if I have log to the base a of b, this is equal to log to the base c of b divided by log to the base c of a, where c is a conveniently chosen base. Spoiler alert, in calculus, the c is usually going to be the number e. So if we have something according to another base, we'll often want to convert that to base e, and this would be how we would do it if we're dealing with logarithms. Let me give you an example of why that guy is useful. Let's say I wanted to find log to the base 4 of 8. Now log to the base 2 of 3, log to the base 2 of 8 was simple. We saw that was 3 because 2 to the power 3 was 8. It was very nice to see. But 4 to the power what gives you 8? Right? You might say 4 to the power 1 is 4, 4 to the power 2 is 16, right? So I already jumped past the 8, right? What power will actually give me 8? It has to be a number between 1 and 2, but what is that number? Right? So what do I have to raise 4 to in order to get 8? Now there are a couple ways you can think about this problem, but the change of base formula is probably one of the easier ways you can do it. Because I know about both of these numbers in terms of base 2. Right? So one thing you can realize is that I can conveniently put in base 2 by using that formula. So I don't know what 8 is in base 4, but I know what both 4 and 8 is in base 2, so let me throw in the base 2. In order to apply the base 2, I use the change of base formula. Now, what is log to the base 2 of 8? That's 3. Log to the base 2 of 4?
2.
That's 2. So the answer is 3 over 2. And you can check it. 4 raised to the power of 3 over 2 does give you 8. If I take 4 to the 3 over 2, that's the same root as the square root of 4 cubed. That's the same as 2 cubed. That's 8. Okay? So using this formula, we can actually figure out logs that we don't know. So these rules I've given you so far are super important. You should have all these first five rules memorized. There are other rules that can be derived from the above. With relative ease. So technically you don't have to memorize them, but I would recommend you do. It'll make your life a lot easier. So let's talk about rule 6. What if I put the number 1 here? What is log of 1? Yeah, it's going to be 0. Why? Because a raised to the 0 power gives us 1 by the exponential rule that we had earlier. So log of 1 is always 0. As long as your base is a valid base, it doesn't matter what particular value it is, it will always give you 0 when you plug in 1 into the log. Right? So log to the base 2 of 1 is 0, log to the base 3 of 1 is 0, log to the base e of 1 is 0, log to the base 17 of 1 is 0. Log of 1 is always 0. What is log of 0? Yeah. Well, if I put 1 here, what are you saying? You're saying a raised to the 1 gives you 0. But that's not necessarily true. A raised to the 1 would give you a. Right? And 0 is not a valid base for a logarithm. We always want positive numbers down here. And so for our purposes, this is undefined. Log of 1 is actually not defined. And we'll actually look at the log function to see why this is. So log of 0 is undefined. Once you're hitting the log of 0, it means you're going somewhere that you shouldn't go. So by the definition, we can see that log of 1 has to be 0. Once we have a valid base, any base, log of 1 is 0. Log of 0 is undefined. And another one is the following. So let's say you have log to a base, and it's so now let's say I put an exponential function inside of a logarithm. Okay? But the base of the exponential function is the same as the base of the log. What is that going to be?
Is it just x?
It's going to be the power. It's going to be x. Right? Why? Because according to that rule 2, I can take this x and I can bring it down in front. And according to rule 1, then I'd have log to the base a of a, but according to rule 1, that would be the number 1, because a raised to the 1 would give me a. So I have x times 1, x would actually be the answer. Right? So if I plug an exponential into a logarithm, they kill each other. And I'm left with the power. Seems like something convenient, but let's continue. It's useful to know that that actually works the other way around. Let's say I have an exponential function, and in the power I put a logarithm of some number. It turns out that is also the number x. Which means if I plug an exponential into a logarithm, they kill each other. And if I plug a logarithm into an exponential, they also kill each other. When two functions share those kind of relationships, those two relationships, what do we say about those functions? What do we call such functions? Right, so let's say I have two functions f and g, f of x and g of x. And if I take f of g of x, I get x. And if I take g of f of x, I also get x. What do we call f and g? Yeah.
Inverses?
They're called inverses. So it tells us that the exponential and the logarithm are inverse functions. They're inverses of each other. Now that should automatically tell you how to draw the graph, if you remember how inverse functions, the graph of inverses relate to the original functions. Okay? Which we'll get to very soon. Now, not really a rule, but more of a notational consideration. This is like everything up to like Calc 3. If I have the basis e, we actually call this a special notation. Does anyone know what that is?
Natural log?
It's the natural log. What is the symbol for it?
ln.
It's ln. Right? So throughout the semester, I'm going to be using this function a lot, ln x. You should be aware it's just a log function when the base is e. And log of x, and again, this is in lower level classes. It's not the same when you go for a while. Log of x, if they don't write it, would be log to the base 10. This guy here is the standard logarithm. And the standard changes based on the discipline you are. So eventually, if you go high enough in mathematics, E is so standard that this symbol represents ln. So if you're reading a very high level math book, whenever you see this, it's really ln. If you're reading a computer science book, this means base 2, right? Because binary. Right? Most people know this though as base 10 because it's with engineering and science. We have 10 figures. We count in base 10. So it would refer to base 10 unless you're in a very specialized field. But for our class, I'll write this all the time, ln x. It's called a natural logarithm. Right? Because it's created from the base of the natural exponential function. aka we read it as L and X. So whenever I say L and X, I'm talking about that. Let me just finish off with the graph. We'll do a little bit of computation with these at the beginning of next class, but for now, let me just finish off with the graph. 8 and 9 also suggest the following. The graph of a logarithm will look like this. Y equals log to the base a of x, where your a is bigger than 1. It will pass through 1 here. And we know that because of how inverse functions work. Because inverses. So we know that an exponential function is this guy, that's y equals a to the x. To find the graph of its inverse, you would reflect in the line y equals x. So if I take this, flip it into this mirror image, I would get that guy. Right? So knowing the graph of an exponential, we can automatically figure out the graph of a logarithm. You will notice that this never touches 0, therefore this will never touch 0, which tells us that log of 0 is undefined. There is no value where it's going to hit the y-axis. Right? And this tells you that log of 1 is always going to be 0. So we have that graph. And we can, again, do all the transformations. Alright, so y equals minus log. I flip that upside down. So it will look like this. Or if you look at y equals log of minus x. Look like this. That one will look like this. We'll stop there. We'll do a little bit of interaction between logs and exponentials later. You can check the suggested problems. And right after that, we'll jump right into calculus. But we're going to use a lot of these functions, so I wanted you guys to know what it's about. Remember, we have a quiz later today. Good luck. I will see you. Oh yeah, give me the questionnaires that we filled out. Thank you.